Okay, we want to look at a graph and see what this idea of average rate has to do with a graph. So I've got a graph of some function y equals f of x. Actually, I don't have a graph of the function. What I have is a graph showing 2 points on the graph of that function. And let's say this is all I know. Okay, well, then let's see, the average rate, I'll say average rate of change of y equals f of x with respect to x is change in f divided by change in x. Okay? So what's the change in x according to this graph? Well, right here is the change in x. Here's the first one x value, here's the other. Here is change in x. Now I'm going to use delta for the change, so I can write delta f over delta x, so I don't have to write out all these words. So here I have delta x. Now what about delta x? Well, let's see. Here's a value of f, and here's a value of f. Now, if x changes from this to this, well, when x has this value, f has this value. When x has this value, f has this value. So here I have my change in f. Which I can write just as a good delta f. Okay, delta f, change in f. I could also write that as change in y. So I could write this as change in y divided by change in x. Because y equals f of x, this is also the change in y. So there's a depiction of the change in x and the change in y. Now how could we depict the change in f divided by the change in x, which is the average rate of change of f with respect to x, determined by these two values? Okay, well, let's see. I'm going to go to the delta y over delta x. The delta y between these 2 points, well, actually I'm just going to give it away because there's no obvious way to do otherwise. At least I can't think of one right now. Okay, well, here's the change in f, here's the change in x. And let's motivate this a little. What if the rate of change was less? For the same delta x, I'd have less change in f. So my point would be maybe here rather than here. What if this point is the same and this point is further up? Well, that's going to give me a bigger change in f or change in y for the same change in x. So the further this point is above this one, the greater the rate of change. The further this point is, well, the closer this point is above this one, the less the rate of change. If this point is lower than this one, actually it looks like I'm going to have a negative change in f for a positive change in x, and that's going to give me a negative average rate of change. Well, we can kind of cut through all that by sketching a triangle. Where this leg of, and this is going to be a right triangle, the legs of this triangle are going to be parallel to the x and the y axes. And I didn't do a very good job. I didn't draw that quite straight across, but you understand what's intended. And that's not delta y, that's delta x. Okay, so that this leg, this side being parallel to this side, and these projection lines here making right angles with the x-axis, and we implicitly assume that you understand that. then this leg of the triangle has to have length delta x. So we have a delta x here. Now delta x has a direction, and delta y has a direction. Okay, so what do we have if we divide the delta y by the delta x? There's a name for the thing we have if you think about this triangle, and if you've learned pre-calculus in any way other than by applying a bunch of formulas, and I believe you probably wouldn't be in this course if you hadn't, but if you did learn it that way, it's okay. We can fix that easily enough. Okay, we got delta y here, delta x here. Delta y divided by delta x is, well, I'm going to say it's just the slope of this line. Okay, because the slope of a line segment is its rise divided by its run. And we have a rise that corresponds to delta y, a run that corresponds to delta f. And of course that could also be delta f over delta x. Okay. Furthermore, if this point has coordinate x, this point has coordinate x, starting to write my delta, getting ahead of myself, x plus delta x. And, well, the coordinate here would be f of x. The coordinate here would be f of x plus delta x. Now, I didn't leave myself room to write that because I didn't know I was going to say that because I didn't plan carefully enough. So I'm going to say f of x is this value on the y-axis, and f of x plus delta x is my value on this axis. So that delta y equals f of x plus delta x minus f of x. Here's x plus delta x. Here's a point on the graph, so this has to have a y value that's equal to f of x plus delta x. This point corresponds to x value x, so this y value has to be f of x. From here to here, the change is f of x plus delta x minus f of x. So we can also note that slope is delta y over delta x, which is delta f over delta x, which is f of x plus delta x minus f of x over delta x, our difference quotient. And our difference quotient, therefore, represents the slope of this graph. It also represents the average rate of change. And we'll say that's the average rate of change of f with respect to x. So our conclusion, and it's a big deal, slope between 2 points of the f of x versus x graph represents the difference quotient which in turn represents what? The average rate of change of f with respect to x. So we have this correspondence between the slope here and the average rate of change of f with respect to x.